you divide something by its length, it makes it length 1, right? That's basically, in my physics class, I'd say this is g hat. You know, it's g hat. And so that has length 1. Okay, so then this has the norm of fn is equal to 1 for all n. Yeah? So what he says, thus the sequence fn is not convergent to 0. So therefore, now why did we want, okay, so, well, fine. So the norm of fn minus 0 is not going to 0, right? The thing is, that has to, this has to be something that's true for arbitrary norms, right? So what he's using here is that
there's an it, so it's like the norm of it.
yeah.
Which contradicts the, wait.
So why is this a contradiction?
Because we had earlier that.
I don't.
He's claiming that flexibility itself tends to 0 for all n and from t. Nothing just
He says, on the other hand, it's easy to see that fn of t goes to 0 for every t in 0, 1. Why is that easy to see?
because then it keeps shrinking down.
Right. Because in the limit, you can take n sufficiently large to make the values sufficiently close to 0 for arbitrary t in 0 to 1. Basically, this shrinks to a point. I mean, this is not even the, that's not the graph of fn either, you know?
So it's like the top of the spike going down to 0 as well as it increases. It's the function of.
See, I guess we don't really know exactly because we can't know that because this is a hypothetical norm we don't have a formula for, you know? I think there's a small gap there because okay, so fn of t is what?
It's just g sub
Gn of t, right, over the norm of gn, right? So if you think about this formula, are we good? Okay, good. So obviously, so here, down here we have a graph, right? So like, clearly it's 0 for, you know, fn of t is equal to 0 for all t greater than or equal to what?
2 to the minus n.
So if you take the limit as n goes to infinity, t goes to 0,
Yeah.
and that's a constant sequence of 0, so it's
Oh.
something like that is the argument.
Okay. Oh.
Yeah. Yeah. I think this example will come up again as we talk about uniform convergence more, but so that brings us to the equivalence of norms. When did I start in here? What time did we start? Do you remember?
3:15. Oh, on this. Sorry.
Oh, you're fine. Oh, I'm an hour in. So it's up to you. We could go another 10 minutes if you want.
It's up to you. Whatever you think.
I better stop here because I gotta get to church tonight. So,
Okay, yes, sir.
but this is a good place to stop. So next time we'll talk about the equivalence of norms. So what we learn next time is that on a finite dimensional vector space, all of these different notions of norm give you the same convergence.
Oh, okay. So
And-
even though you can apply different norms on a single vector space, they're all equivalent and finite.
Yep, and more than that, also in this section, like topology is defined in terms of like open, closed, those things. That's later in this section. And in fact, if a set, so like you can define open and closed in terms of the metric topology. Okay, so like, what do we mean? We're talking about sets with normed linear spaces, right? So any normed linear space can be given a metric by simply using the norm of the difference. Like if I want the distance from x to y, I just take the norm of x minus y, and that defines a distance function, which will
This is a mapping of x cross whatever's the set from x. Yeah. I think I see.
so like, yeah, I mean, the distance function, it's symmetric. Like the distance from x to y is the distance from y to x, because the norm of x minus y is the norm of y minus x.
Right. So it has a symmetry.
It has a symmetry. It has the distance from a point to itself is 0, because the norm of x minus x is the norm of 0, which we proved today is, which we assume today is 0. And
Yeah, triangle inequality for the missing the norm.
right, and yeah, and then triangle inequality as well. And so once you have a metric, you can define what's called the metric topology. So the metric topology is defined, and essentially a set is open if each point is an interior point. To be an interior point means that you can find an epsilon ball defined in terms of that metric, which is induced from the norm.
Oh, okay.
All right, so there's this induced metric topology from any norm that we pick. And the equivalence of norms for finite dimensional spaces, one of the consequences of that is that all of the metric topologies, all of the induced metric topologies from all your different norms, they're all the same topology. It's open in the 2 norm only if it's open in the sup norm, if it's open in the 1 norm. So that's part of the reason this doesn't matter as much. And these things are not true in infinite dimensions. In infinite dimensions, there becomes a difference between these different modes of convergence. So, although not always. So it's subtle. For a long time in my thesis, we couldn't decide whether or not we should be using the 1 norm or the 2 norm for supernumbers. So supernumbers are in some sense like LP space.
Okay.
But they're kind of like the numbers themselves are built from infinite series of terms, where the coefficients are each complex number, let's say, and what is multiplying them are monomials, well, products of Grassmann generators. What's a Grassmann generator? It's this anti-commuting indeterminate. So like eta 1 times eta 2 is minus eta 2 times eta 1.
Yeah.
So those Grassmann indeterminates multiply in a very specific way. It's a lot like polynomial algebra, except it doesn't commute, it anti-commutes.
Yeah. Oh, okay.
So it's, and anytime, like if you have eta 1 times eta 1, it's 0.
Yeah.
So many things collapse to 0 in these products of Grassmann's, but we'll work with a set of supernumbers such that the norm is finite. But the question is which norm, because you could either use the one that's built from like adding together just the modulus of the coefficients, which would be like the 1 norm, or you could add together the square root of the squares of the, and that would be like the 2 norm. And I think for a while we thought that these were different, but in the end, I think in the end we became convinced that they were equivalent. But now that I talk about it, like what did we really remember? See, because when I try to go back and find the records on it, I'm always like not sure until I really start digging into it.
Oh.
So it's aggravating. But I have another conjecture, which is that so do you know about Quaternions?
I haven't studied them setting too much. I've heard of them, but no, I haven't studied too much of them.
Okay, so like Quaternions are kind of the the best finite dimensional analog to supernumbers. Because quaternions are built from things of the form like T plus, let's say AI plus BJ plus CK, where here IJ is K and KI is J, and I squared equals to J squared equals to K squared minus 1. So it's kind of like 3 copies of the complex numbers stuck together, paired with a set of real numbers, such that they all interact. And it's really neat. If you multiply 2 quaternions, this is a quaternion. If you multiply 2 quaternions, what you'll find out is that the product, the scalar part of the product is the dot product, and the vector part of the product actually is the cross product. So the quaternion multiplication simultaneously folds the dot product and the cross product into a single algebra. And the people who love this sort of thing refer to it as geometric algebra because it's geometric algebra. I'm not a geometric algebra person, but I understand those people in their way. So one of the interesting things about the quaternions is that it is almost a field.
Okay.
What's a field?
Well, a ring with the multiplication operation having unity.
Has a unity, yeah, has addition, multiplication. They behave like normal, right?
Yeah.
And every non-zero element has a multiplicative inverse, right? That's what makes it a field. It's not just an integral domain. It's an integral domain where, everything's a unit, except for 0. Everything has a multiplicative inverse except for 0.
Oh, right, yeah.
And it's a commutative ring, right? It's a commutative ring. That's what a field is. So in the quaternions, actually, every quaternion has a multiplicative inverse except for 0. So, but the reason it's not a field is that the multiplication is not commutative. See, because I times j is equal to k, which is equal to minus j times I. I guess I didn't tell you that, but so it anti-commutes.
Oh.
So quaternions are not a field because they're not commutative.
Okay.
But everything else that's field-like holds for quaternions, in the sense that it still has like distributive laws of multiplication. It has a norm, which is multiplicative. There's a notion of norm of quaternions, that the norm of ZW is equal to the norm of Z. Oh, wait a minute, is that right? Yeah, I think that's right. My bad. Yeah, this is important for your number theory?
Sadly, no.
Okay, that's okay, but
Sorry.
no, yeah, you're fine. So the quaternion norm allows you to derive something called the 4-square identity. So it's very special. The fact that you have a multiplicative norm, very special. For more abstract algebras, you don't usually have a multiplicative norm. It's really special to have a multiplicative norm, which is to say that the norm of the product is the product of the norms. You know it, you love it, you take it for granted with complex numbers.
Yeah.
The norm of ZW is norm of Z. I mean, I'm saying norm, but I mean modulus, absolute value, depending which professor you talk to, right?
Right, yeah.
So that's special. For arbitrary abstract algebras, associative algebras, we found that the norm is submultiplicative. So it usually is less than or equal to some number times the product of the norms. Not so with the quaternions. They're very nice.
Is that like Cauchy-Schwarz kind of?
It's related to that. So these supernumbers I'm telling you about, I conjecture that they're like the quaternions. I think that they're actually an infinite skew field, in the sense that every non-zero supernumber has a multiplicative inverse. But I haven't proved that. So I'm still, I think it's true.
Is that your main research focus?
Oh no, it's just a question sitting around there. I haven't really actively worked too much on supernumbers for a while. I have some questions in topology that I'm interested in answering there. But I have to find students. I mean, I usually only work with students, you know, so I'm waiting for another student to come along who wants to look at my supernumber topology question. And Audric is not that interested, so which is understandable, because it's, I don't know. I'm interested in finding submanifolds of a supermanifold which have topology, non-trivial topology, like curled up dimensions in the part of the space which is not the commutative part. So like, I think it's possible in the formalism that I work. I don't think it's possible in the mainline formalism. Mainline formalism takes every supermanifold to be a vector bundle over the base space, which means that the topology of the supermanifold is the topology of the base space. In contrast, the kind of supermanifolds that I work in, there doesn't have to be a strict relation between the topology of the base space and the topology of like the weird new part. So yeah. So I'd like to come up with more examples that exhibit that weirdness. And so like that's one of my standing problems, to come up with more examples. So, and I think a good student, undergraduate student of topology is going to help me with that someday. And it might be Audric, if I can get him interested in it. But anyway, yeah.
I do have one.
Well, yeah, go for it. Any questions?
This is probably back to a little bit non-interesting stuff, but with the function d sub n of t, where it's saying the norm of d sub n is never 0, because d sub n itself is not 0, I think is what it says.
That's right.
But if t is 1 and n is 1, do we, since in the second term it's piecewise, then we get,
So
does that give us 0?
if n is what? If p is what?
If t is 1 and n is 1.
T is.
If n is 1.
Oh, okay. So, all right. So here we must separate in our mind the distinction between the function having a value which is 0 and the function being the 0 function. See, the function norm is 0 if and only if it's the 0 function. The 0 function on 0, 1 has to be identically 0 from 0 all the way over to 1. That never happens for any specific value of n, because there's always this tent. For a finite n, there's always this tent. Yet in the limit, it's gone.
Okay.
Weird.
Okay.
That's the nuance.
Oh, that's what gives us that's the whole thing.
Yeah, yeah.
Okay.
So, but at the end, it's not 0 because there's always this tent. Yeah.
Okay. So
Yeah.
it's
Yeah.
identically the norm is 0.
So, well, thanks. I enjoyed today, and sorry, Audric, you couldn't be with us, but at least you could watch this on double speed since you already know this stuff.